Can you define the word creating for me? I'm unfamiliar with it.
Okay, so this, yeah, I got you. This first meeting, I'm gonna
No,
actually.
the officer that I told.
Okay, anyway, this first meeting, I'm gonna talk about the theoretical aspects of neural networks. The actual part where you learn what they do, not how to write them. This is useful because everyone has written them already. You have lots of APIs, you have libraries that you can download that does all of this for you. So first thing that's up is you actually have to learn how to use them and how they work. So, ready? Let's go. Welcome to my TED Talk. Actually though, I'm not qualified in any way, shape, or form.
This is not financial advice.
Yes, not financial advice. I just love coding and I love these aspects and I've researched, I've had fun with this. So, let's get started. Okay.
Oh wow.
What do you see here?
Numbers.
Yes.
Okay, that's
Zero.
true.
Digits. Really.
So what I want to do by the end of this, and one of the simplest and easiest tasks to get a hold with neural networks is digit detection.
Okay.
What digits are here?
504192.
Okay, good. Now, we have computers.
Alright.
Your brain can easily recognize these numbers as it has been evolved for years and years. Someone tell me, how do you think a computer can recognize these digits?
It will look at them and be like,
I know,
which matches the most with this picture?
No,
which number
I
matches?
know.
But they're all handwritten. Yes, Divya.
You tell the computer, you give it like a billion variations of a 5, and then it closely checks each one of them.
That's literally practically what I said.
Okay. So yeah, that's kind of what our goal is here. The computer will learn itself. So take a look at this number. What is
It's
this?
a 0.
Okay. How do you know it's a 0?
Because it looks like a 0.
Because you've written 0 a bunch of times, and you know that's
Okay,
the
so
general shape.
we can take this. The way the computer will read it is we can turn it.
That's cooler, guys. Come on.
We can turn it into smaller and smaller parts. Hi. I'm lecturing. Okay.
He's a PhD in
I'm not.
He has a
This is
PDF.
part of the 0. We can get the computer to read this specific part, and then together combine it with the other 3 parts, creating our big 0. This is how we want our computer to read the.
so it's just gonna
0.
identify them by the.
So it specifically first puts it into separate parts.
Yeah.
This is where we start to get into neural
This is
networks.
a 0, right?
Yeah, it's still the 0.
Okay.
Because it's been split up 4 times.
Yeah.
And then we'll split up each of these images again and again and again.
Okay, that's cool.
Yes, Divya.
Wait, didn't it? I know this from like the 3 blue 1 brown video, but didn't they
Yes.
say that's not what computers do?
Exactly. This is how our brain works. This is what we want for a computer to do.
Okay.
Unfortunately, they don't actually do this.
Oh.
And the way, because there's no easy way to tell this to the computer and make it do it. So we make the computer learn by itself. How do we do that? That's right, math.
I love the
that's
enthusiasm.
my whole thing. Okay, so this will get us into our actual part about neural networks. That was the introduction. Why are they called neural networks? Does anyone know?
Because they're like. About the brain.
Because they learn like the brain's neurons.
Correct. That's why this field is called machine learning.
Okay.
We get the machines to learn, and overall, it should learn by itself. We shouldn't have to put in much info. Our neural network.
Great.
So, this is the basic model. Rosenblatt, the creator, this is called a perceptron, proposed a simple rule to compute the output. So he introduces weights. I'll get to you in a sec, not yet.
Okay.
Introduces weights, and basically what this will do is it will take in any number of inputs. Doesn't have to be 3. And based off these inputs, it will give you an output.
Okay.
All inputs will be 1 or 0, and the output of this will be 1 or 0. You can already start to see how you can combine multiple of these to create a larger network that can start to do decision making. So
Decepticon.
let's start with. Okay. So for us to do this, for it to determine the output, we will do what's called a weighted sum.
Okay.
One of the best ways to think about each of these decisions are as vectors. Now this is tough, this is difficult, so we'll just put something simple where we say the sum of the 3 vectors will give us our output. Okay? And if it's greater or less than some threshold value we have. To show this, these are our two equations. Okay. So as you can see, we have our two decisions. We will consider them as vectors, at least for this.
Cool.
And you will basically add them up together. And if they get over the threshold value, less than, then we'll give a 0. If it's over, then we'll increase it to 1.
Okay.
This is saying like true or false, determining the other two topics. So, imagine you want to go to the pool.
Okay.
Wow, look at that. That's a swimming pool, right? That's a
Yeah.
pretty cool swimming pool. Now, a couple of things are that to make this decision, you want to weigh up all the factors. Factor number 1, you want to know if it's raining. Okay? Who wants to go to the pool when it's raining?
No one. Divium.
False.
Because you get wet.
Exactly.
Yeah.
Can you believe it? Getting wet in the swimming pool?
It's ridiculous.
Number 2 is if you have friends who want to go with you.
What if you're going to swim laps by yourself?
Exactly.
See?
Yeah.
That's boring.
So
No one
it
does that.
determines, and then lastly, if they're selling your favorite snack.
Oh,
Okay.
right. Okay.
So you can add up these by determining how likely you want to, with each of these, you'll want to go to the pool. For example, do you want to go to the pool when it's raining?
No.
Yes. We don't really want to do this. Here, let me just skip ahead. You can see they all combine to make your decision. So if we don't want to go to the pool when it's raining,
Yeah.
what we can do is we can add a weight to this. Normally, each of these are perceptrons. They will return an output of 1 or 0. If it's
Okay.
raining, output of 1. If it's not, 0. We'll assign a weight that tells us how significantly this will impact our decision. For example, we don't want it to rain. If it's raining, we don't want to go to the pool. We'll assign a weight of 6.
Like
Which-
6 is how much you don't want to, or 6
Yes.
is like, okay, all right.
How much you don't want to if it's raining. So if it's raining, this will output in 1. I'm sorry, I'm done. If it's raining, it'll output in 0.
Okay.
If it's not raining, it'll output 1. So this is a big decision, a big factor in your decision of going
6
to
is
the
like
pool.
its importance level.
Exactly,
It's like 6 out
its
of 10,
importance
right?
level.
It's out of 10.
No, I'll get to that in a second.
Oh,
This
okay.
is considered its weight. Then we have for snacks, let's say you don't really care too much at 2. Same with friends. You're fine going to the pool by yourself.
Okay.
So now with these 3 decisions, you have to create what you want at the end. Well, if you want to go to the pool or not. This is where we get into the threshold. As you saw before, these are your 3 vectors, and they need to go over the threshold value. So let me pull that up quick. Well, are we going to put our threshold to over 5? Which means, if it's sunny outside, well, you want to go to the pool.
Yes.
Yeah.
Sunny, no snacks, no friends.
Yeah.
Yes.
Just like my life. Yes, you will want to go to the pool, because 6 times 1, that's going to be greater than your threshold value of 5. Now, if it is raining currently, but your
Yeah.
friends and you have snacks, will you want to go to the pool?
No.
Wait, what if it's, so pretty much everything will work as long as it's sunny?
Yes, for now, because this is
Okay.
your decision.
Only going whether it rains.
The
or
point
not.
is, this is an example. You can then change this weight to, let's say, 3, change the threshold to 4. 4 or greater allows you to go to the pool. That means that you can go with friends or snacks, even if it's raining. Into some more math.
Yay.
I love math.
I don't.
So this is where you change the threshold to 3.
Okay.
So that means even if it's raining, you can have friends or snacks, and you'll be fine to go to the pool. So, math. We want to simplify our equation for the perceptrons. This is what it was before.
Okay.
What we can do first is, because these are vectors, we can get the dot product.
Got
You
it.
guys like dot product, right? Math 5, Math 5,
Wait,
Math 4,
what's the dot
sorry,
product
anyone?
again?
Math that's called a basically equal. They're not exactly
Oh, yeah,
equal,
yeah.
but they're basically equal.
Facts.
That's a thing that gets used in higher level math. I've had to use it for some other things as well. Second thing is we want to remove our threshold. We want to make threshold to 0. So what we'll do is we'll inverse that, and we'll give ourselves B. Now what is B? Let me remember, 'cause I
Negative
forget.
threshold.
So yeah, B is the negative threshold.
It's 3, right?
Yes, so in our last example, B was 3. This is what we call the bias.
Okay.
This is like threshold, except we put it to one side of the equation. So that we get something simple like that.
Okay.
And that makes it easier for us to do math with this later on. Okay. So with that example, this isn't exactly how we make decisions, as I said, but it shows the basis of how the neural network will work. And as you can see, you can add a bunch of these decision-making models together to give you a full network that will give you an answer to your question. I'm kind of slow at this, but yes. So this is our first layer.
That's like all
This
of
is our
the-
second layer.
Okay.
This is the final for this example. What is this second layer doing?
You don't know.
Computing, it's like the hidden layers because you don't really see it. So just
Yes,
like
but what does
computing
it do in this
How
example?
do you know that actually?
It's
He's
It
done a
takes
little
the
bit.
inputs from the first layer.
Exactly. Takes the inputs from the first layer, and it will give a new input. This can be used to make more complicated models that will combine together to give you a better output, instead of just one singular perceptron. Okay, so there is a problem with the perceptron, and that is it can only give you outputs from 1 to 0. The way neural networks work is that we will change our weight based off the neural network gets the answer correct or wrong. If it gets it wrong, then we want to change the weights till it adjusts and gets it correct.
Okay.
That seems a little complicated, but that is basically how we want it to do.
Yeah, like, but like, you know,
So,
it's like
what is
0
it
to 1,
that
it's like
Small,
5, it's like
small changes in the
PDF
weights
works.
will completely change your answer. For example, in the last example that you saw, we had the 3 pool, rain, and whether you want to go to the pool or not.
Yeah.
We changed the weight of the rain even a little bit. We changed that to, let's say, 5.
Got it.
Immediately, even if it's raining or not, it doesn't matter. You're not going to the pool,
Right.
right?
Yeah.
So we will get into our next type of neuron.
You should.
So, sigmoid neurons.
Yay.
We depict it the exact same way,
Oh, okay.
but it's different. Because instead of having an output that's 1 or 0, and an input that's 1 or 0, the input can be from anywhere between 1 and 0. That means you can have an input of 0.65321. But just like the
Sigmoid.
perceptrons before, these sigmoid neurons also have weights and biases. They're used in the exact same way, just they can have a value ranging from 0 to 1.
Okay. Cool.
So, this is our function for the sigmoid neuron. You saw our function before for the perceptron, which is the dot product of W and X plus the bias.
Yeah.
All you do is slap a sigmoid function on that. Sigmoid function is a cool function that will give you values ranging from 0 to 1. This
my trip back from New York.
is your function.
How?
This is your function here. This is the sigmoid function.
Oh, ha ha ha.
When you look at it immediately, it's like, what is this? So basically, it does something pretty simple. When the original value is big that you're adding into that z, it will make the final number approximately 1. It will get closer to 1 as the value gets bigger and bigger. When it's negative, or very small, it will get closer and closer to 0. Okay? This can be seen in our sigmoid function graph. Our previous perceptron function. This is called a step function. As you can see, if you have a simple change from positive to negative, it flips the entire neuron. Compared to our previous sigmoid function, it will
Yeah.
give you a value in between. Okay. So a couple more words for terminology. This is called your
Input layer.
input layer, exactly.
And then the second one's like the computing layer?
The middle layer is called the hidden layer.
The hidden layer.
It's called the hidden. It's called the hidden layer because you don't get direct inputs nor direct outputs. You're giving them to other neurons.
It's
Okay.
like private variables.
And
Wow.
finally, the last one is called the output layer.
Even-
Okay.
Yeah.
So
No.
what we're currently doing is called a feed forward neural network,
Yeah.
Forward propagation.
which means the data is always being fed forward. Data gets from the left to the right to an output. there are 0 loops. There are other models called recurrent neural networks, which use loops, but they are less influential. I can't speak currently, because the learning algorithms are generally less powerful for these recurrent ones.
And also,
Recurrent nets are less powerful, as I said. What they usually do is they take the data, they put them out, and then they put them right back in. They use the same data again and again using the exact same.
Are they more?
Current neural networks currently are just less powerful,
Okay.
is what I've seen from them. I haven't done much research, but currently with what we have, they're not as powerful as what we're doing. So now that you know what neural networks are, we can get on to our problem.
yay.
Digit detection. Okay.
Oh, right, I forgot about that. That was like in the beginning. I like
Yeah.
it. It's like a boomerang. It came back.
This is what I'll by the end of next week you guys should be able to write your own
Oh, nice.
based off
okay.
what I've given. So there are 2 problems in digit detection.
Yes.
What are they?
It's like they don't read it as. Okay,
Oh,
no,
those
I
are
take
my-
it back. I
oh,
take it
I
back.
have
Okay.
a problem.
We have 2 problems.
Let me-
No, wait.
Ashwin, not Ashwin.
Ashwin can't answer.
Yes.
He's
V
good
has to
answering
answer.
the whole time.
2
okay.
problems.
My turn?
You have to
Yes.
ask like other
If you
people.
get
It's because
given
like
this.
it's because like the thing that we talked about in the beginning, where they're like, oh my god, humans see it differently. That's a problem, right?
Oh, I thought I made a problem coding it.
Okay, whatever.
Yes. Problem
I
coding.
take it back. I don't.
Finding
I don't
the right
participate.
We
data
have
set.
I
no, not
volunteered
that.
to participate.
Finding a right
Okay,
data
because there is not one part to this problem. If you're given this, what is the first thing you have to do with
break
this?
it up into separate numbers.
Exactly.
But
Break
it's
it up
given to
into
you in the
separate
data
numbers.
set. It's literally given to you in the data set.
No, but you have
That's
to
not
break
the
it up
problem.
into
But the
separate
No,
point
no,
is-
but like if you just turn in one, it's like a string. If you
The
turn in
point
one
of the
string,
final neural network is
Unless
that you
you
should
take
be
it.
able to classify
But the thing is, the
a
computer
whole
doesn't know
range
that
of
it's
digits,
like a string.
even if they're together.
Right? It doesn't know where one ends and the other begins.
Exactly. It doesn't know. All it sees are pixels on a screen.
Are we detecting like the entire strip of digits or just one?
just
It's
I will get
one
into that.
image.
Like
So-
they're just analyzing.
The point
the
is,
image.
by the end, our neural network should be able to classify a whole strip. It shouldn't just be singular numbers. First problem is that it's actually pretty easy, and we don't have to worry about it, because there are many ways to get that past this problem, and one of it is just by putting it into our neural network. We can randomly decide a place to cut the number, and if our neural network is not sure at all that that is one of the numbers in its database, we can then change where we cut that number. So, I think I have this image up here. Yes. If this is the thing, and we have our neural network completely working, it knows how to classify 5s and 0s, and it gets this image. It shouldn't know how to classify it off the bat. It should be very unsure about what it's giving you. And that we automatically know that that's probably a sign that something is wrong in where we cut it. So, we can cut it to where it gets to a
Wait, so we cut it ourselves?
single digit.
We cut it.
We do not.
Okay.
We randomly, I don't know exactly how it goes into it,
Okay.
but you can take a portion of the thing, and if it's sure that it's a digit, it will give you a nice output,
Okay.
and you should be done with that part. If it's not, then you can change how you cut it.
All right.
Okay. And then the other is the actual way we recognize the individual digits.
Whoa.
Boom. This is a small model. This shows the original outputs, a single hidden layer, and output. Currently, we have 784 neurons for our input layer.
Yeah.
Why is that? Well, because we're going to be using images of 28 by 28 pixels, which means each of these neurons will be taking in an individual pixel.
Okay.
Okay? So, well, for simplicity, they're not all here. You can see there's a number. And what these will be taking is the color of the corresponding pixel. If the color is completely white, it will return 0. If it's black, it will return 1. And any shade of gray in between will return a point value in there. That's why we're using Sigmoid neurons. So our second layer is, again, our hidden layer. Here you have 15 neurons. Technically, you can increase this, decrease it. The more it has, usually the better it will be. But that that doesn't matter right now. We can later test with different values for our n. And finally, we have our output layer of 10 neurons. Why do we have 10 neurons?
Because we started with 10?
To represent the
Did
digits.
we even start with 10?
To represent the digits,
Also, it
exactly.
should-
So again, how does this work? What is the basis?
So you get a picture,
Mhm.
and then each of those pictures, like each pixel on the picture, gets like a whiteness to blackness like scale,
Okay, yes.
and then you input that as a number into each one of those neurons, so you get all the 28 by 28 pixels, which is 784. Then it goes to the hidden layer, and the computer
does
does
it-
its thing. And
What does it do before that? What are the two necessary things for this?
weights
Neurons.
and biases.
Yes, weights and
So
biases.
you give the computer, to start with, you give it like, you set all the weights and biases to
Around
near
zero.
zero,
Around 0, exactly.
and then
That's to be properly balanced.
it like sends it to the hidden layer, and then the hidden layer does the same weights and biases thing from the near zero stuff, and then it does its own thing that you don't know, and then it sends it to the output, and it gets the wrong answer the first
What
time.
if you...
So yes, we output between 0 and 9, and it changes its weights by itself. This works by determining which of these has the, for example, if you get a value of 0 at the end, let's say the sigmoid, after you do the sigmoid function through these layers, you get a value of 0.6. What we can do is we can create it so that if the value is above 0.5, that is considered its correct value.
That makes sense.
Yes. Okay, that is basically all I have for now.
Let's go.